All right, in part 2 here, we're going to kind of finish our discussion of fast Fourier transforms. And what I want you to kind of get from this series of videos is kind of a high-level overview of what these transforms are and kind of how to use them. So we kind of cover the idea of a transform. So we can actually use integrals to transform any signal into something else that may be easier to work on in another domain. So you can use any function for a transform, but sines and cosines tend to be what appear a lot in nature. So that's why we have Fourier. And last, in this video, we're going to try to get to the fast aspect. You know, where does the fast aspect comes from? But the reason we're going through all these steps is that, you know, oftentimes when you learn in signal processing, there's a few key points that I think, you know, students miss, that so you can understand how you use data that comes out of these algorithms, because it's really not that hard once you understand it. So let's bring up the Fourier transform again. So I have a signal, P of t, pressure of time over time, maybe it's a microphone, and I have a result, P of f, that shows how well you know, a signal is correlated to some frequency. And if you remember, a complex exponential, right, you can break it down into a cosine and a j sine term. So all we're really doing when we use a complex exponential is we're actually kind of doing you know, correlating against two different signals, a cosine and a sine. And the reason is if we have a signal, you know, we want to get phase information, and to get that, we have to compare it against a cosine and a sine, something at 0 and 90 degrees, and that's all that means. Now, we don't have to use cosine and sine. It turns out you can use other functions. It's just when you decompose signals, it's very useful to use sine and cosine. So what you get out of here is another function. And what that function does is it shows you at any frequency, and I'll just kind of draw it like this, how well correlated, you know, the signal is with the sine or cosine. So these peaks might show us frequencies where it's highly correlated. Now, this function plot is not equal to this. So we tend to look at what's called the magnitude. But you can also look at phase. The result we get out of here, P of f, is a complex number. It has a real and an imaginary part. And that's key to understanding what comes out of a Fourier transform. If it has a real and imaginary part, we can look at magnitude and phase. So in this case, here's a magnitude plot, and that's what we usually look at, are the magnitude plots of how you know, of the correlation. So that's an important distinction. The output of this, you know, is a complex valued function, you know, because we have a complex valued input. So let's take the next step. So this is in continuous time. This is actually kind of useless to us in you know, the digital world, because we can't do, for example, this. Negative infinity to infinity. We don't have that. The other thing we don't have is time. We usually have, you know, an index n, you know, which is related to some delta t. We have samples at different points. So the next step that we look at is what's called the discrete time Fourier transform. I'll say that one more time. The discrete time Fourier transform. So let me throw it up here real quick. So this, if you look up, and you can look at any reference text, you know, the first step here is what's called the DCFT. So we have discrete time Fourier transform. And the only thing we did is we said, let's say we have a function P of t, and let's look at it and sample it at intervals delta t. And we have a sequence, P of n, you know, where n just represents multiples of t at delta t time steps. So if we do that, what we essentially do is we can get rid of the summation or the integral and go to a discrete sum. So that is always the first step in understanding the FFT, is going from continuous time Fourier transform to this discrete time. Now we have to do one more step. Because we sample some sequence at delta t, that inherently says that we have like an upper limit to the bandwidth that we've captured in that signal. So going from n equals negative infinity to plus infinity, let me circle that, it's kind of dumb. Plus, that is not computable. Like, we don't need to look for all frequencies known to man. As soon as we sample it, we've automatically band limited, constrained our problem. So that's the DCFT. So there's one more step we need to take. All right, and that next step is just something we call the DFT, the discrete Fourier transform. Now, DFT, all these things you can look up in Wikipedia. There's very good explanations, albeit mathy ones. But here's what I want you to take away. And one thing I want to apologize for is I do switch around some nomenclature throughout here. Is sometimes I use 2 pi ft. In other places, I just use omega for 2 pi f. I switch around cyclic and radial frequency, but just think it's a variable, a frequency-based variable. So in this case, to go to a full discrete Fourier transform, I have a signal p of n. I kind of like this array notation because it's similar to like the C language, which I like. But instead of going to infinity, we go to big N. We have a discrete number of frequency points, that we want to hit. And because of that, each of our frequency points is 2 pi f little n over big N. So what that means is 2 pi f, that's like the biggest frequency. And what we get out of this is another set of data points, p of f, that is a discrete set of complex numbers. All right, p of f is just a set of complex numbers, like 0 plus, j1, 0 plus, j2, 1 plus j3, where each one of these numbers shows, for example, the real part is a number that relates how well our input signal is related to a cosine wave. The imaginary part represents how well our signal is correlated with a sine wave, 0 and 90 degrees. All right, so we have two numbers. Now, the key is understanding how do you interpret those numbers, the real and imaginary part, because oftentimes you don't look at real and imaginary. So let's bring a plot. So if I have a real axis, an imaginary axis, and let's say we have a point, and this is some p of f. Actually, I should draw it in brackets. It's discrete. Let me kind of draw this out here like this. If we draw it on the complex plane, we get a vector. All right. Remember, we said this point is how well we're correlated with a cosine wave at that frequency. And here is the value is how well we are correlated with a sine wave at that frequency. Well, the first thing we care about is just how well is it correlated in magnitude. So that's just this right here. That is, the magnitude of P of F. Now, magnitude, that's just vector magnitude, all right? That is just the real part squared plus the imaginary part squared. Take the square root of that. It's just the norm, the length. Now, we can also take the phase angle, all right here. Boop. This angle to this vector is the phase angle of the sine wave of the wave that your input signal is correlated with. So that is all that means, the real and imaginary terms. They just show, for example, how well we're correlated with cosine however, correlated with sine. So if we take the phase angle, that gives us the angle of a sine wave that our signal is correlated with. And then the magnitude of these numbers, this squared plus this square root it, it gives us the magnitude of the sine wave component. And so that's what you do with the data. And that's so whenever you take a discrete Fourier transform, you get complex data out, but that's what you do with it. You know, you can basically calculate the phase angle and the magnitude to get something useful. Now, we still haven't answered the question of fast. All right? What does fast mean? Well, the DFT, you know, you can compute that. You could actually come up with an algorithm to compute it. But it turns out, if we look at this, there is a lot of multiplies and a lot of adds. So the way you'd compute this is simply break this up into the e to the j in the real and imaginary, a cosine and j sine. You do the multiplications and do the real parts, sum up the real parts and sum up the imaginary parts. That is a lot of multiplied adds, but you can do it. So where does the fast part come from? Well, that's where the FFT comes from. The FFT is simply just a DFT, but it is just a special implementation. It's a special implementation. And what the FFT does is it makes some basic assumptions. The algorithm makes some assumptions about your signal, all right? And using those assumptions, it can reduce the number of multiplies and adds you need to do the computation. So really quick, let's just talk about what those assumptions are. All right. The first assumption is, and we kind of assumed it, and I didn't really say we assumed it, is that the input sequence, the first assumption, you know, is real valued. All right. Now, not all FFTs require this. Some do. There's actually some optimizations you can do if we have a real value. So let's say we have real value. Second, all right, if we're real valued and the size n is a power of 2. All right, so that means our input sequence is 128, 256, 512, so on and so forth. In the second one, it turns out we can get away with the real valued and still get an efficient algorithm that's better than a straight DFT. But the big one is that we have a power of 2. Now, why is that? So what the FFT does is, let's say we start off with a 256 DFT. What the FFT does is it breaks the signals down into two 128 sequence lengths and says, well, what if I had to calculate the DFT of these signals? All right. Well, it turns out if you do this enough, I'll just draw it here. You can eventually get down to where you're just calculating a bunch of smaller DFTs, and then there's a way of backing all of this out to get the large DFT. All right. Now, in another video, I'm going to point you to a reference that shows exactly how that works. But right now, I don't want you to get bogged down in that. It's just that the way the algorithm works, and the reason we need a power of 2 is that if we can take a power of 2 sequence, we can always keep cutting it in half and compute DFTs of the half sequences. All right. And then if we keep doing that enough, we'll eventually get to a small enough sequence where we can do some magical things that take less multiply and adds. All right. So what this is eventually called, this process is, you may see this, is a radix 2 algorithm. And what it's eventually trying to do is break these up so we can do a lot of 2-point DFTs and then have a neat way of backing them out. Now, there are some other interesting things, is if we have a power of 4, meaning our input sequence is like 4 to the n, there are other algorithms, one called, like, for example, the radix 4, that does some neat things that if we don't have power 4 to also be computationally efficient. But you can actually, radix 2 is kind of like the end of the pipeline. This works. All right, so that's just a term you might hear. But so that's why we need the power of 2 input sequence, because that's the way the FFT works. Now, you can search on Wikipedia on how the FFT is actually computed. It's actually pretty simple. There's some interesting things that happen in terms of reversal of the input pattern and whatnot that has to occur to make it happen. But it's actually a neat algorithm. You can do some searching on it. But what I want you to take away is that for the FFT to be it's just a fast input. It's just a DFT. All right. It's just a fast version of it, and it's a special implementation. And the big deal we have to know that is it's a power of 2. Now, a power of 2, if we have a power of 4, for say what's called a radix 4 algorithm, or a power of 8, a radix 8, there's some other optimizations, but think power of 2. Now, the last couple things I want you to keep in mind is that about an FFT. So we're going to put in, kind of this discrete sequence. I'll do it as an array. And we get out, complex valued numbers. And right now, I'm only going to consider, to make things simple, real input sequence goes to a complex, output sequence. Now, because if our input sequence is real, one thing that happens with the transform is that, and I'm going to draw kind of frequency, and I'll draw like an amplitude. Let me draw that line there. And I'm going to try to do this carefully. Let's say I'm going to start drawing, and this is our plot. All right. It turns out that if we have a real input signal, we get complex, we actually get a mirror image in the magnitude in the data. And it turns out that this mirror image happens at Fs, the sample rate over 2. And that's actually kind of interesting, because you think about it, if we're correlating against all these sine waves and we have an Fs over 2, that kind of makes sense when we think about the sampling theorem. That means if we sample a value, if its sample rate is, say, 40 kilohertz, we can see the spectrum from 0 to 20, because that's all we can capture. And that's kind of like something that falls out from this concept. Now, the reason it's a mirror image is because our P of F over here, this is like the first set of, the first half of my output. The other half over here, P of F, the reason the magnitude is a mirror image, because essentially we get the complex conjugate on the other side. So really, what I want you to take away from is, we look at the FFT, if say we get 100 data points in, we might only get 500, I'm sorry, let's start over. Let's say we put 1,024 data points in, all right? Now, we don't get 1,024 useful data points out. We only get 512 because of this Fs over 2, because of this complex conjugate. Really, in terms of real information, we're only concerned with, say, the first half of that array, the first half of the set of complex numbers. And once you understand that P of F, is just a set of complex numbers, and I'm using whole numbers here to make it easy. That what we get out of that transform is a set of whole numbers. We can take either the magnitude of those numbers, or we can take the phase. We can calculate that phase angle from that. Now, a lot of times, if we're looking at a spectrum, we may not care about phase. There might be applications you certainly do, but in this case, we do not care about phase. So, in the monkey listen, we in the monkey listen visualizer, we usually look at spectrum. We want to look at the amplitude. What are the components? We don't necessarily need the phase. So, in the source code that we're going to take a look at later, we calculate the FFT, but we only look at the magnitude part. So those are some things to take away. Now, the idea here is this is supposed to be a broad overview. So don't take this as this is the end of the road. There's a lot more. Now, let me show you, bring in some cool videos, some other references. So the video I want to show up in it's on YouTube. It's called The Fast Fourier Transform Algorithm by Barry Van Veen. He actually has, through his university, a lot of different signal processing videos I highly recommend you look at, but this really dives into how we actually go through the computation of the FFT, what are called the butterflies, in reversing the inputs, the signal to make the FFT happen. So I would, if you're really, really interested in how this works, take a look at this. And I'm going to include this in my YouTube playlist because I definitely didn't want to recreate this. He did a very good job. So the video here, I just wanted to give you a very high-level overview of how we get to the FFT and what do we do with the data. Because really, at the end of the day, that's all that's what we care about. So I hope that you found this useful. And, this is the last part on looking at any of the theory. In the other videos for the monkey listen, we are going to look at, the source code and a specific implementation of an FFT algorithm with the SimSys DSP library. So I hope this was helpful. Talk to you later.